Okay, I am going to go ahead and pass around the sign-in sheet just so that you, so that I know who's here and who's not here. The yellow and orange just is telling me what section we're in, but that doesn't matter as you'll see going forward. It's just, I'm still trying to find out if anybody's added or dropped my class. So, don't worry about the yellow and orange, is what I guess I'm trying to say. Okay. So what we're going to be doing today is we are going to be, first of all, I'm going to continue with another example problem related to the Clausius-Clapeyron equation from last week. I only got to do one in lecture last week, so I'm going to go ahead and do another one. That way you have a couple of examples to work from. The second thing I want to do is then we're going to move into talking about heating and cooling curves and how to calculate the energy associated with the changes in temperature associated with certain materials. And we are going to pull in some of the stuff you learned last semester, such as Q equals MCAT at that point. But anyhow, we're going to do heating and cooling curves, and then we're going to do phase diagrams. Now, the way I normally run a lab lecture is I will lecture for about an hour and then take about a 15-minute break and then lecture for about an hour, so that we have a little bit of a break in between to kind of recharge. So any questions about the plan? Okay, then let's go ahead and get started into the material we were covering on Friday. Trying to think of what day of the week I'm on. Okay, so we were talking about the fact that when we look at vapor pressure is actually a curved line when you look at increase in temperature compared to the vapor pressure. So change in temperature versus vapor pressure. And so we can take this curved line and apply some algebraic concepts to it in order to convert it into a straight line. And when we do so, we get the Clausius-Clapeyron equation. And the Clausius-Clapeyron equation is the natural log of P2 over P1 is equal to the negative delta H of vaporization over R times 1 over T2 minus 1 over T1. Okay, so on Friday, I did an example problem where we actually calculated the delta H of vaporization. Let's look at calculating another piece of this equation. So in the next one, we have the delta H of vaporization for hexane is 28.9 kilojoules per mole. Normal boiling point is 68.73 degrees Celsius. What is the vapor pressure? at 25.00 degrees Celsius. Okay. So thinking about the Clausius-Clapeyron equation here, because what we have is we've got two temperatures and two pressures. Let's look at what pieces of information we know. We know the delta H of vaporization. That delta H of vaporization is 28.9 kilojoules per mole. Now, you may go, well, what is P1? The answer to that comes in this term right here, normal. When we're talking about something that is normal, that tells me that P1 is going to be at 1 atmosphere. So again, that term normal is telling us what the first pressure is going to be, because that's going to be at 1 atmosphere. Now, at that pressure, we have a temperature of 68.73 degrees Celsius. And we have been asked, what is the vapor pressure at a temperature of 25 degrees Celsius? Well, to finish this out, we are going to need our R value. Our R value is 8.314 joules per mole Kelvin. The reason we are using this particular R value is because it is the gas constant that involves energy, which the unit for energy is joules or kilojoules. Now, that R, remember, is a dictator. It tells you what the units need to be in. And if you look at our R value, the unit of R is in joules. That means the energy values need to be in joules. So the first thing you need to do is you need to convert this kilojoules into joules before you start doing your math problem. That way all of your units are matching up. Okay, so now that we have that, we can use our Clausius-Clapeyron equation. Yes, we do. Thank you for, I would have noticed once I put it in, because that's one thing you need to do is you need to be very cognizant of using units. And I would have noticed when I started going into my temperature that, oh, wait, my units don't match. But yes, you do need to change your temperature units into Kelvin as well. So we have 298.15 Kelvin, and we have 341.88 Kelvin. Okay, now that we have everything, we're ready to plug everything into this equation. So the natural log of P2 over 1 atmosphere is equal to a negative delta H of vaporization, so a negative 28,900 joules per mole, divided by our R value of 8.314 joules per mole Kelvin, times 1 over T2. T2 was 298.15 Kelvin, minus 1 over T1, which is 341.88 Kelvin. So plugging all this into the calculator, we get a natural log of P2 over 1 atmosphere is equal to a negative 1.4913. The opposite of natural log is the exponent. So if we take the exponent of both sides, that means the P2 over 1 atmosphere is going to equal e to the negative 1.4913. So you get a P2 over 1 atmosphere of 0.225, and therefore P2 equals 0.225 atmospheres.
What's the E?
E is the exponential, or not exponential. Yeah, exponential. It's if you look at it, you can always tell what's the opposite of something on your calculator, because if you find the natural log button, you'll notice the E is right above it. So you need the second of the natural log, and that will give you the E. It's just the opposite of a natural log. It's the way to get rid of natural log. So the way I have it written, those would cancel out. Other questions?
Change the HVAC to joules over moles.
Because if you look at R is the gas law constant. Constants are dictators. They tell you what unit everything else has to be in. So since the R value is in joules, we had to change the kilojoules so that they matched up to joules.
Square rooted P2 over 1 ATM.
I didn't square root it.
Or you square rooted 1 ATM, right?
No, that's just a mess. It's just 1 over 1 ATM. So basically, once I got the E value, it's just a mess. It's the pen. Other questions? But thank you for asking, because I don't want it to be confusing. Basically, the Clausius-Clapeyron equation allows you to calculate the enthalpy of vaporization if you know both pressures and both temperatures. That's how we determine the enthalpies of vaporization for many a substance. If you know the enthalpy of vaporization, you can calculate an unknown pressure. So basically, you can figure out these numbers that are on this graph up here based off of the temperature and the pressure. So a change in temperature equals what? Change in pressure. Okay. So now what we're going to do is we're going to talk about heating and cooling curves. And when we're talking about heating and cooling curves, we're talking about for a single substance. Okay. The first thing I want to do is just talk about the heating and cooling curve as a whole. Then we'll get to where we apply mathematics to that heating and cooling curve to understand our energy changes. So that's the plan. First, I want to describe a heating curve. Let's think about water to start out, because it's the easiest substance, because we have the most experience with water. If you have water at 0 degrees Celsius, what is that? That's the freezing point or the melting point, however you want to say it. Everything below that is ice. Or in other words, it is in the solid form of water. Now, when you get to 0 degrees Celsius, what you have is you have a mixture of solid and liquid. Basically, what's happening is if we go back to our thoughts on the structure of a solid compared to that of a liquid, what we see when we have that melting is that we basically set up an equilibrium between these two. Some of the solid or some of the intermolecular forces break. To form the liquid. Simultaneously, some of the liquid reforms the solid. So you set up this equilibrium between the solid and the liquid at the melting point. And it takes time for all of the solid, for those intermolecular forces to go ahead and dissolve, in a sense, to make liquid. This occurs at what is known as the enthalpy of fusion. Now, I showed you that you can have the enthalpy of fusion as well as the enthalpy of freezing. These are the same value. Except they are opposite in sign. When we have freezing, we're going to have a negative delta H. It is a negative delta H for this component here because energy is given off during freezing. By the way, at any time while I'm talking about this stuff, if there's a question, ask. Don't wait. Go ahead and ask.
If fusion's negative, does that make freezing?
Well, freezing will be the negative because I'll show you in a minute. Let me go back to the graph and talk through the graph, and then we'll come back to this and do it in the opposite.
So you said that these two values are the same thing, which is the values like for wet state of that we go to.
Exactly. Enthalpy of fusion and freezing are the exact same numerical value. They just are opposite in sign because it is depending upon whether energy is being absorbed to go from a solid to a liquid, or whether energy is being given off as you go from a liquid to a solid. Because remember, signs with respect to enthalpy don't mean the same thing as they do in a typical algebra class. Signs, when we're talking about enthalpy changes, what they are describing is whether energy is given off or whether energy is absorbed. So it doesn't mean quite the same thing as it does in an algebra class. It's describing the directionality of the absorption or release of energy. Okay, going back up here. So it takes time for all of these intermolecular forces to begin to break to form a liquid. So that's why we have a straight line. It's because it takes some time. Now, once we get into liquid form, we're going to see the temperature increase again. Because now we have liquid water. And what temperature does water boil at in degrees Celsius? 100. So you have your boiling point. So at the boiling point, we have to break all of the intermolecular forces now. That quantity is known as the delta H of vaporization. The opposite of that would be the delta H of condensation. So, I should have done, let's do it this way so that I actually can keep up. So with this second piece, all of the IMFs break to go from liquid to a gas. However, simultaneously some of the gas molecules will lose enough energy to revert back to the liquid. Just like with our delta H of fusion and freezing, the delta H of vaporization is equal to the delta H of condensation. They tend to be opposite in sign. And again, that is because as gases condense, energy is lost. Questions so far? Now, folks, the delta H of vaporization is much bigger than the delta H of fusion. Anybody want to propose a reason that the delta H of vaporization takes much longer than the delta H of fusion?
So you have to break all of the bonds.
Because you got to break all of the intermolecular forces. And that takes a lot more energy. So your delta H of vaporization is a much larger value than the delta H of fusion will be. Now, one reason I wanted to explain that these delta H's of fusion and delta H of freezing are the same value is because a lot of times we just say delta H of fusion. And you're supposed to know, is it the negative version or is it the positive version? One reason I just made sure that you know delta H of vaporization is the same as delta H of condensation is because a lot of times we just say the enthalpy of vaporization. We don't give you the enthalpy of condensation. We just say the enthalpy of vaporization. And you're supposed to know that they're opposite in signs, depending upon whether you're absorbing energy to make a gas or whether you're giving off energy to go from gas to liquid. Now, once that enthalpy of vaporization has occurred, now we are in our gas phase, and again, the temperature can increase and it can continue. What I just drew for you is a heating curve. When you look at the heating curve and cooling curve homework, you're going to see I always start by drawing a curve. And the key components of that curve is this 5-segment line, the melting point, and the boiling point. Because you're not going to know what calculations you need to perform unless you know what the melting point and what the boiling point are. You're not going to know what calculations to perform unless you know what segment of line you're actually, moving through. So that's why I draw it out. And then I go back and do some, you'll see on the homework, I even took green pen, which you'll be able to see because it'll be downloaded. And I highlighted the color just so that you can see that it underwent changes. So I tried to be very specific. Okay, so folks, if I want to draw a cooling curve, it would essentially be the same. I would start out with what is my boiling point? What is my melting point? The only difference is now I am cooling it down. So it starts out at a hotter temperature. My delta H of vaporization is here, but it's going to be a negative value. I'm going to cool that once all of the gas is converted into liquid, it'll cool down further until we get to the melting point where you get your delta H of fusion, which again would be negative, and then it would continue to cool from there. So the cooling curve is just really opposite. It's cooling curve because you're starting out at a hotter temperature and you're generally cooling it down. Questions about the curve itself and why. So, key points. One of the key points about the cooling curve is, I'll do it as a question and answer time. What represents what line, what piece represents the conversion of a solid into a liquid at essentially equilibrium? What piece of the heating and cooling curve represents a solid and a liquid that are there simultaneously? The delta H of fusion. Why is the delta H of vaporization much larger than the delta H of fusion? Takes more energy to break all of the intermolecular forces. What line represents the presence of liquid and gas simultaneously? Delta H of vaporization. The segment of line that is, whether it's increasing or decreasing, that you see below the melting point is what? In what state of matter? What? It's a solid. Whether I used ice because ice and liquid and gas, we all steam. Those are things that we're comfortable with, but this will be useful for any substance. So we could talk benzene, we could talk acetone, we could talk isopropyl alcohol, anything will fit into it. Speaking of that, what do you expect to be the difference? If I were to give you, if I were to ask you to draw a heating and cooling curve for another substance such as isopropyl alcohol, what do you think would be the difference here? The temperatures. Our melting point and boiling point. That's what would be different. The fact that we have solid, here I wrote ice and water, but the fact that we have solid, liquid, and gas, that would not change. The fact that at the melting point, it's in both solid and liquid form, and that's the delta H of fusion, that would not change. The fact that at the boiling point is a liquid and a gas, and it's the delta H of vaporization, that would not change. The only thing on here that would change is what those temperatures were. Questions for me? Okay, let's get into a problem. I'm gonna make up, do I have all the stuff to make up a problem? No, I don't. Okay, actually, before we can get into a problem, we have to do one more thing. We need to talk about how to do the calculation at each segment. Segment 1, segment 2, segment 3, 4, and 5. Okay. You actually already have some of the tools that you need to perform these calculations. At segments 1, 3, and 5, you will use the equation Q is equal to MCAT, which you worked with in College Chemistry 1, where Q is equal to the heat, M is the mass in grams, delta T means T final minus T initial. And the only change is our specific heat. And you may or may not have applied the state of matter to the specific heat in College Chemistry 1. You will have the specific heat of a solid, the specific heat of the liquid, and the specific heat of a gas. So that's the only difference that you have to pay attention to, is what is the form of substance you have at that point. Because the specific heat needed to raise the temperature by 1 degree Celsius of 1 gram of material is going to be different. For example, for water, it's around 2 point something for the solid. Meaning you only need a little over 2 joules to raise 1 gram of ice by 1 degree Celsius. For the liquid, which is what you did in lab, it took 4.184 joules to raise 1 gram of water in liquid form by 1 degree Celsius. And then I think it's 2.01 for the gas. So again, you have to pay attention to the specific heat. Now, 2 and 4. Yes, you'll see an example here in a minute where I give you all of the pieces of data and then you have to know what to apply when. For 2 and 4, your heat is going to be equal to the moles times the delta H. And again, it'll depend upon whether what you're dealing with, whether you're dealing with the delta H of fusion or the delta H of vaporization for the enthalpy. And that's going to allow you to calculate your heat associated with that particular step. So let's look at an example. Okay. How much energy in kilojoules is required to melt 220.1 grams of ice at negative 25.67 degrees Celsius and bring the resulting liquid water up to 75.91 degrees Celsius. Okay. I told you, first thing I'm going to do is draw my heating and cooling curve. Oh, I guess I need to give you data. Let me give you the data first. C for the gas is equal to 1.84 joules per gram degree Celsius. C for the liquid is 4.184 joules per gram degree Celsius. C for the gas is equal to 2.09 joules per gram degree Celsius. The delta H of vaporization is equal to 40.7 kilojoules per mole. The heat of fusion is equal to 6.01 kilojoules per mole. Now, if this is a different substance such as isopropyl alcohol and benzene and stuff like that, I would also give you the melting point and boiling point. But for water, I expect you to know those.
Is the first one supposed to be the heat of the solid?
No, the last one was. The 2.09 should have been the specific heat of solid. Thank you. Again, if it's benzene, isopropyl alcohol, acetone, whatever, I would give you the melting point and boiling points as well. But if it's just water, I expect you to know those. So the first thing I'm going to do is create my heating and cooling curve. I know that water has a 0 degrees Celsius melting point, and I know that it has a 100 degrees Celsius boiling point. The general format is always the same for a heating curve. Now, I am drawing this as a heating curve because I went from a lower temperature to a higher temperature. So I'm drawing, so I know because of the change in temperature that we are dealing with a heating curve. Once I've drawn my general heating curve and have my melting point and boiling point, now I pay attention to those numbers. So I am starting at roughly a negative, well, I'm starting at negative 25.67. And I'm going to 75. It doesn't matter that it's not perfectly, the unit or the increments are not perfect. This is just helping me mentally figure out what I'm supposed to do. So I have to pay attention to the first step in the cooling curve, heating curve, the second step in the heating curve, and the third step in the heating curve. I don't need number 4 and number 5. I didn't go past 100 degrees or even to 100 degrees. I stopped. Now, so step number 1 is going to be Q is equal to MCAT. But I'm going to be using the specific heat for the solid. My Q is equal to the mass, which I made up as 220.1 times the specific heat of the solid, which was 2.09 joules per gram degrees Celsius, times my change in temperature, which was T final minus T initial. Now, for this segment, what is the final temperature? It stops at 0. Because again, we're going up. So it stops at 0. So 0 is our final temperature minus our initial temperature of a negative 25.67 degrees Celsius. Or in other words, our Q for this section is going to be 11,808 joules or 11.81 kilojoules. For the next step, we are in the delta H of fusion range. So our heat is going to be equal to the number of moles times the delta H of fusion. Well, the first thing we gotta do is convert that 220.1 grams of water into moles of water. Which is 12.23 moles. So that we can apply it to this equation.
That should be 18.
2 hydrogens at basically 1.00794, and 1 oxygen at 16. So 16 plus 2 is 18. So I rounded because I'm doing it all in my head. 12.23 moles times our delta H of fusion, which was 6.01 kilojoules per mole. And you get a Q of 73.49 kilojoules. I'm paying attention to my units, folks. The entire step. I give you the equations. You got to know when to use it. And what sign you need to have for the delta H of vaporization or fusion, depending upon whether it's a heating curve or cooling curve.
So you get 0.49, like I got 7.33.5.
I probably, because I took the entire number I got the first time of 220.1 divided by 18, it's technically 12.227777778. And I never took it out of my calculator.
We wouldn't get cut off.
No, as long as we're close, it's usually around slight rounding difference, and that would have been what we would have been the difference. 3, the third step in this process was that liquid. And therefore we're going to use Q equals MCAT, but we're going to use the specific heat of the liquid at this point. So Q is equal to the mass of 220.1 grams times the specific heat of liquid, which is 4.184 joules per mole joules per gram degrees Celsius, times the change in temperature. Our final temperature at this one was 75 degrees Celsius. Our initial temperature, again, if you look at this line, the initial temperature started at 0 here, because we're only looking at this segment. So it would be minus 0 degrees Celsius. Which gives us a Q of 69,067 joules, or 69.067 kilojoules. Now the question, if you go back to the actual question, it asks for how much energy is required. Well, the energy required, there is a fourth calculation. The energy required is going to be equal to 11.81 kilojoules plus 73.49 kilojoules plus 69.067 kilojoules. Or in other words, we're talking about 154.4 kilojoules to perform this this transition. It is positive because it was a heating curve. Meaning energy had to be added to cause the transition. Questions? Yes.
If we were doing a cooling curve, whenever we were using like, I know it doesn't say it here, but the 2 and 4, the straight lines on the graph, is that when we would put in the negative?
Yes.
Okay.
And to be quite honest, if you are doing Q equals MCAT properly, where you're taking T final minus T initial, it's going to help you figure out what sign you should use because they will always come out correct.
So even if we like put in the negatives for our enthalpies, we still at the very end need to make sure to have that negative sign if we're doing cooling curve. Or like if you work it out correctly.
For a cooling curve, everything would be negative.
Okay. So even at the end, we wouldn't have to worry about like make sure you put your sign, like if we did the math right.
If you did the math right, it should all come out negative. And so you would get a negative energy because you would be giving off energy. Okay, so I actually went 7 minutes over my hour, but I don't like, again, I feel like you can only sit for an hour and then you got to have a break. So we are going to take a break and we're going to come back in 15 minutes. So 12, just make it 12:05. My brain doesn't want to do the extra math. And if you have questions and didn't want to ask in front of people, now's a great time, however you want to do it. I love questions, but y'all can go get snacks from, you have time probably to even get to the student union if you need lunch. How's it going? Trying to recover from the weekend? Me too. I usually only have 2 people in my, and 3 dogs in my house, and this weekend I had 11 people in my dogs in my house. So. Yes.
That one is going to be you can guarantee one of them will be able to put it room temperature because it's going to have the higher boiling point. Or, I mean, the higher melting point.
The stronger, which one is the strongest force?
Now, you talked to me about number 20, and I did delete number 20 because it was asking for something weird. I'm still not certain what it was asking for when it said the first.
I had someone else to talk to you about.
Yes. Because I was looking at the change at the delta age of vaporization would come into play if we would use, talking about the blended. Okay.
So. CF all the same, so it's
Correct. And HCl was the only other possibility. And it has cycled by itself.
And then this one was carbon dioxide CO2.
Right.
Whenever I did it. It had one pairs, right?
Actually, carbon dioxide, because of the real rules. I tried to give you a simplified version, but if you actually do the Lewis structure, carbon dioxide has 2 double bonds to the oxygens. That's the only way oxygen can get its full oxide, and so it becomes money.
That was weird.
I wouldn't say it's weird. It's just, it was, when I gave you the rules to try to speed up how you look at things, the rules really don't apply to things that have double bonds and triple bonds. And so you've got to kind of know. So the only way to get to the double bonds and triple bonds is by doing the actual Lewis structure and going through all the steps. So when I was trying to help you speed up the mental process, I did not go over double bonds.
Okay. So CO2 is double bond.
CO2 has 2 double bonds.
So it's polar.
No, because it's linear.
Oh, wait. Yeah. Linear is non-polar. So anything non-polar is non-polar.
Correct. I will be right back.
What would have money for
Everything has it because electrons are in constant motion and that's the basis of London dispersion. The only time I typically get to take off London dispersion is I
I typically don't check it off with ionic compounds, but even ionic compounds have London dispersion. They just don't necessarily have hydrogen bonding.
And if you have hydrogen bonding, you have dipole dipole.
Yes.
If you have hydrogen bonding, you have dipole dipole hydrogen bonding. And
Correct. Now on active, they're usually just looking at the strongest forces.
right, this one's comparing to. This one has hydrogen bonding, but the other one is CH3, CH2, CH2, Cl.
Okay, so it's probably half.
Dispersion and or dispersion and dipole dipole.
Correct.
Why is the one I just said have dipole dipole?
Because that one,
Chlorine, what does the chlorine do?
it makes, it's, first of all, it's not a very big molecule, it's only a 3-carbon molecule. And then for that chlorine, because it is much more electronegative atom than carbon and hydrogen pulls on the electron part.
This one says CH3, CH2, CO2, H.
Those both have hydrogen bonding.
Okay.
What that CO2H really looks like. Yes. Busy. It wasn't too bad. Like I said, I went from having only 2 people and 3 dogs to having 11 people and 3 dogs in my house.
Wow. It's like family dinner?
Friends
Oh,
and my daughter. My daughter's in and all of her friends come in.
that's so nice though.
So, but it wasn't bad. It was a lot just because I'm not used to it.
Did you spend your time? What else y'all do?
Played games, played D&D. I made ribs, which is like a labor of love because it takes me about 10 hours to make the ribs. So I spent a lot of my time cooking for 11 people.
Yeah. That's awesome.
Hopefully y'all had some fun and got some rest here and there.
So every compound is CH, like different amounts. The biggest one
Is the strongest.
I got it. We can get it.
That's why it was wrong.
Okay, folks, I'm going to get back to it. The second part of today is actually going to be shorter than the first part of today. Okay, it is recording. I thought So what we're going to discuss now is actually things that, I mean, you can get a lot of information out of it. And we're going to discuss discuss a phase diagram. When we talk about a phase diagram, it is similar in some regards to what we were just talking about with heating and cooling curves. But when we talk about a heating or cooling curve, we're looking at a change in temperature at a constant pressure. With a phase diagram, we're looking at a change in temperature with a change in pressure. You're going to have calculations to do with the heating and cooling curve like we've been doing. But with a phase diagram, it is more about interpreting the graph with respect to how I'm gonna pose questions. So just to kind of give you an idea of the way the questions will be posed. Okay. So we've already done the heating and cooling curve. Let's deal with phase diagram. For phase diagram, you're going to have temperature on the x-axis, and you're going to have pressure on the y-axis. They'll look a little bit different, but they're going to have generally 3 quadrants. Well, 3 sections. The left-hand section is going to be your solid. The middle section is going to represent the liquid. And the right-hand section is going to represent the gas of a material. So we're talking about, when we're talking about phase changes, we're talking about changes in states of matter. Now, in this diagram, this point where you have a solid, you have a liquid, and you have a gas, that point is referred to as the triple point. And folks, on the lecture videos, the flipped classroom videos, and I hope it's still linked. If not, let me know. There is a link when it says phase diagram up at the top. It's underlined, therefore it's linked. Click on that link because there's a really good video that can illustrate all these different states of matter and what it actually looks like at these various points. Now, up at this top hand point, this point up here, everything else is going to be a supercritical fluid. And what a supercritical fluid is, it is a material in which you cannot discern a liquid and a gas. What that means is that the liquid molecules are just far enough away that they appear gas-like. But the gas molecules are just close enough together that it appears liquid-like. And that is what a supercritical fluid is. Supercritical fluids are difficult to obtain because they typically are at extremely high pressures and temperatures. But once you get to those high pressures and temperatures, you can start to see this state of matter where it's very difficult to discern whether you've got whether you've got a gas or whether you've got a liquid. They're going into both phases pretty regularly. And it's really hard to discern them at that point. Now, when I did the delta H of vaporization for water previously, that was assuming pretty much normal pressure. And again, if it says at a normal pressure or a normal melting point or boiling point, this normal means we're talking about something at 1 atmosphere pressure. So when I was doing the heating and cooling curves and we had a enthalpy of vaporization of 40.7, that was probably the normal boiling point. But if you look at this line of temperature here, a boiling point means you're going from a liquid into a gas, correct? So this line represents the delta H of vaporization at different temperatures and pressure. Just like this line represents the delta H of fusion at different temperatures and pressure. Because it is at that line where you go from a solid to a liquid. So right now, all I've done is just talk about definitions. I will give you a relatively normal phase diagram to work with. Meaning that there will only be the three sections, the solid, the liquid, and the gas. You can actually get some that are kind of crazy. But I will make sure I give you a relatively common phase diagram to analyze. What type of questions can be asked from this general phase diagram? Well, I could ask, what states of matter exist at the triple point? All three. What states of matter exist in this region? Liquids and gases. You will be expected to fill in solid, liquid, gas on your own. Now let's look at some more questions, but to do so, I've got to be able to, I got to draw another diagram. Okay. I'm going to let you catch up to me drawing a graph. And then I'll give you some questions. Okay. If I were to ask for the normal boiling point, I told you normal occurs at 1 atmosphere. And well, I should say, the first thing I do when I'm given this problem, and I'm just given this, I label my sections. Solid, liquid, gas, supercritical fluid, triple point. Now, if I say the normal boiling point, what does that mean it has to be at? 1 atmosphere, because I use the word normal here. So you're going to sketch over, and normal boiling point means we're going from a liquid to a gas. Whoopsies. So I'd sketch over to that line. And on this one, I would say it's around 375 for me. Yours may be different because of us drawing, but normal boiling point means that you went to this point right here. And I'm going to try to help keep these separate. I'm going to put that as number 1. If I ask for the normal freezing point, that's going to be that line. And so I would trace it down and go, well, that's at around 150 degrees Celsius. Now, as long as, number 1, when you're doing this, as long as I can see that you know what you're talking about, if our numbers differ, that's going to be expected, because there's a lot of variation between 300 and 400. I estimated at 375. You may have said 370. As long as it's not outrageous, like 400. Well, I might have given 400, but I wouldn't have given 425. It would have needed to fall between 300 and 400. But as long as it fell between 300 and 400, I would have given it to you, simply because I know that as long as I know that you knew what you were doing, our difference in opinion could have been the cause of the variation there. So I do try to be cognizant that, as I'm just trying to see if you know what you're doing. What if I said state or states of matter at 0 degrees Celsius and 0.75 atmospheres? Well, that 0 degrees Celsius and 7.5 atmospheres puts it right about here. So in other words, we would have a solid at that particular state. Another possibility is what transition occurs at negative 100 degrees Celsius when the pressure drops from 1 atmosphere to negative 0.05 atmospheres. Well, in that particular case, what you have to do is go, okay, I'm at negative 100 and I'm going to go from 1 atmosphere down to 0.05, which is probably somewhere down here. At that point, I have a solid going into gas phase, or in other words, I have sublimation. These are the types of questions you could be asked in basically, it's just analyzing the graph. Well, I meant positive. Thank you. I meant positive. Because you're right, you cannot go below 0 atmospheres. Okay, which brings up one more thing that we need to discuss. And that is phase changes. So if we have a solid going into a liquid phase, that is simply melting. Whereas the liquid going to a solid phase is freezing. You can have a liquid go into gas phase, which is evaporation. And you can have a gas go into liquid phase, which is condensation. These are common ones we talk about. But you can also have a gas go you can have a solid go straight to the gas phase, which is sublimation. And you can have a gas go straight to the solid phase, which is deposition. So that's why I wrote out solid to gas, but I also identified it as sublimation because you could have used either one. And there also may be questions about what phase changes occur for sublimation or what phase changes occur for melting, stuff like that. So I want to make sure that you're aware of the terminology. Looking back at this, other questions I could have asked, okay, what temperature and pressure are needed to form a supercritical fluid? What that is wanting is, what is this point right here? Because that's the point where you get the supercritical fluid. And so you would trace it down and figure out, okay, that's roughly 825 by, oh, I don't know, 1.85. Or what temperature and pressure do all three states exist? In which case you're looking at the triple point, and you would estimate what the triple point is and try to be a little bit more specific than me, which I get at about 0.8 and 0.65. So again, with respect to the phase diagram, it's about reading it. How do you read a phase diagram? How do you interpret what's going on? I could ask you, what temperature does the delta H of vaporization occur at 1.75 atmospheres? And you would just trace over the 1.75 atmospheres and figure out what temperature it is, where you go from liquid to gas, because that's vaporization. Questions? That finishes up the first chapter. So chapter 11. We skipped chapter 12. I love chapter 12. Don't get me wrong. It's all about solids and understanding solids. But we skip chapter 12 and we go on to chapter 13, which actually gets into solution formation. And since most of the things we deal with are solutions, we're going to spend some time doing that. And so that is where we pick up with tomorrow, is on chapter 13. Yes.